So along came Albert Einstein to try and explain the results of the Michelson-Morley experiment. That when you measure the speed of light, you seem to get the same answer. No matter how the light beam is moving, no matter how you're moving, light doesn't behave like the baseball analogy that Cleo and I just did. Einstein began with two postulates. What's a postulate? A postulate is an assumption that you're going to make. You're going to say, I'm going to assume this is true. I'm not going to prove this. But if it's true, what else logically follows? So he started with two postulates. The first one says this: if two frames of reference move with a constant velocity, so that acceleration equals, if you're moving at a constant velocity, what is your acceleration as a number exactly? So he said, look, I still don't know how to deal with acceleration. Acceleration is still 0. But if two frames of reference move at a constant velocity relative to each other, so they're moving, just not speeding up or slowing down, then the laws of physics will be the same in both frames of reference. He was really saying, I think the laws of physics are the same everywhere in the universe. That seems reasonable to assume. I've never been to Pluto. I've never been outside of our galaxy, said Einstein, but I'm pretty sure that somehow the laws of physics don't change suddenly out there. They're the same everywhere. But why did he say you couldn't be accelerating? He'd already recognized that things behave differently when you accelerate. Like you'd imagine you're all sitting in the passenger seat of a car, and you have a big bucket sitting on your lap, but the bucket isn't full of water. It's full of boiling hot coffee right to the rim, so it's just barely not overflowing. When are you going to get hot coffee spilled on you? When the car does what? It accelerates. He said, look, there's something strange. If you're going at a constant speed, the coffee will stay still, no problem. If you're at rest, the coffee will stay still, no problem. But it's going to slosh when I accelerate. And he said, that's behaving differently, so I don't quite know how to explain that just yet. Or what I wrote here is, in other words, if you pour a cup of coffee while you're on a jet plane that's traveling forwards at 700 kilometers per hour, the coffee still pours straight down. It doesn't pour behind you, even though you're moving forwards. It's going to go wonky if you have turbulence and start accelerating, but as long as you're going at a steady velocity, no problem. You can try this yourself as long as you're not driving. If you play catch in a car, especially if there's two of you in the back seat, if you toss something to your neighbor in the back seat, even though you're moving forwards, you don't have to throw the thing that you're tossing forwards. You throw it straight at them. It behaves in the same way you play catch, in exactly the same way as you would play catch if you were at rest on the ground. If you're accelerating, that's different. I told you that Einstein was famous for thought experiments. One of his thought experiments was to imagine a transparent train or a transparent car. We're actually going to go one step further. We're going to imagine a transparent spaceship. And we're going to imagine that all of us possess Superman's eyes so that we can see objects in detail as they go by really, really fast. They're not a blur. We can actually distinguish things. So he said, I'd like you to imagine someone sitting in a car or in a spaceship, let's start out in a car, throwing a ball up and down like this person right here. If this person was throwing the ball straight up and down, straight up and down, straight up and down, this person would see the ball traveling like this, up and down, up and down, up and down, up and down, up and down. I realize this picture has a tiny bit of sideways motion. Let's pretend that they're just throwing it straight up and down, straight up and down, straight up and down. Hi there, let me pause the video for 1 second. I'd like you to imagine what you would see if you were standing on the road at rest relative to the car. It seems to me, Marcella, instead of seeing the ball going up and down, you would see the ball travel that path because it's moving sideways while it's going up and down. Does that make sense? Can you use your imagination? Does that work okay? So can all of you draw that little upside down V shape down there? That's what you would see. In the car, the person would see the ball going straight up and down. But a person standing by the side of the road would not only see the car moving straight up and down, they would see it moving sideways at the same time, so it would trace out a V shape. Einstein's second postulate, he accepted the Michelson-Morley experiment. He said, I'm going to assume that it's correct, that you will always measure the speed of light to be the same for any observer, no matter what the velocity of the observer is, no matter what the velocity of the light source is. Light does not behave like a baseball. Or, in other words, the speed of light is a constant. He said, I'm going to accept that. I can't prove that it's true, but if it is, then what? This leads to something called time dilation. The word dilation, or dilate, means to make wider or larger, or in the case of time, slower, lengthen it. According to Einstein's special theory of relativity, we call it the special theory of relativity, should really be called the special case theory of relativity. And what's the special case? A is 0. Einstein said, I don't know how to work acceleration. He eventually did work acceleration in, that's general relativity. That took 10 years of heavy-duty math. We'll touch on that a little bit, but the math is ugly, so we're not going to dive into it. But under special relativity, a clock that is moving relative to another object will run slower. And this stretching of time by a moving object is called, in physics, time dilation. So here was Einstein's thought experiment. We're going to imagine a transparent spaceship. The spaceship is going to be traveling forward at a speed v, whatever the heck that is. And rather than a ball bouncing up and down, Einstein said, I'm going to imagine a beam of light bouncing between two mirrors, up and down, 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 up and down. We're going to get a similar effect here as we did right here. I'm going to argue that the astronaut on board the spaceship is going to see the beam of light going up and down, up and down, up and down, up and down. But if we watch the spaceship go past us with our Superman eyes, we would see the beam of light trace out a V shape. Is it possible that in two different frames of reference, identical clocks might run differently and time might pass differently? The answer is not only is it possible, this is one of the predictions of special relativity. So figure 15.6, this picture right here, illustrates an observer inside an imaginary thought experiment, custom-made glass-walled spaceship, made transparent so that an outside observer, let's imagine we're floating there in a spacesuit at rest, can see the spaceship go whizzing by. What would we see? Put your pencils down and look up. So, turn the page, I think. Is that right, I think? This page? Okay. Here's Einstein's thought experiment. And specifically what we're going to focus on is this little triangle right here. What we're going to try to do is we're going to try to write an expression for each of these distances. Now, this right here, don't write this down, that long side, that's the distance that we see the beam of light travel sitting in our spacesuit at rest. This right here, that's the distance that the astronaut on board the spaceship sees the light beam travel. This distance right here, that's how far the spaceship travels forwards. So, we're going to use the idea that distance equals speed times time, if a is 0. Don't know how to work acceleration. And we're going to try to cleverly draw this triangle. So on the next page, where it says DULP. Oh, little note, you're not going to be asked to derive the next few minutes on a test. This is purely for nerd trivia. Where it says DULP, what I'd like you to do is draw a right angle triangle like that. Okay. And we're going to try and put a distance on each one of these sides. And we're going to find that distance by going speed times time. This side right here, this vertical side, that's a beam of light. So the speed is the speed of light. What was the symbol that we used for the speed of light? Loud and proud? So if you want me to write this as a distance, it would be speed times time. That is a distance. This side here is what we are seeing. It's also a beam of light, so we have to get the same answer for the speed of light. So it's going to be speed times time. But here's the problem. We are going to experience time differently from the astronaut on board the spaceship. So I'm not going to use the letter T for both of these. For the astronaut on board the spaceship, I'm going to put a subscripted 0 on his time. Although I don't think of it as a 0 to remember it, I think of it as an O for time on board the spaceship. There's my dumb way to remember this. So that T0 would be if the astronaut had superhuman reflexes and a stopwatch, what the astronaut would time the beam of light taking one path. That T is what we would time the beam of light traveling its path. This bottom leg is the spaceship moving forward. The spaceship is moving forward with a speed v. So it's going to be speed, and it's going to be our time because we are watching the spaceship. This is the observer at rest. It's a right angle triangle. I told you that we were going to use Math 8 and Math 9 to prove this, and we are. We're going to use Pythagoras, which you all do in Math 8. Who remembers the equation or the formula for Pythagoras? It's something squared plus something squared equals something squared. Yeah. A squared plus B squared equals C squared. It's going to be this squared plus this squared equals that squared. As an equation, it's going to look like this. CT0 all squared plus VT all squared equals CT all squared. Einstein started there. Little Pythagoras. Complicated Pythagoras, but Pythagoras. Marcelo, what does it want me to do in step 2? Get the CT0 squared by itself. How would I move this plus VT squared over to the other side? Minus it. So in the next line, I'm going to write this. CT0 all squared is equal to CT all squared minus VT all squared. Nick, what does step 3 want me to do? What I'm going to do is I'm going to put the squared onto there, the squared onto there, the squared onto there, the squared onto there, squared. I think you do your exponent rules in Math 8 and Math 9. So I think this is technically Math 9. And I'm going to get this. Little c squared T0 squared equals little c squared T squared minus V squared T squared. I think so far this is all Math 8 and 9. Cleo, what does step 4 want me to do? So I'm going to go like this. Divide by c squared, divide by c squared, divide by c squared. Equation solving. I did the same thing to everything, so I haven't broken any rules. But I want you to look at that first term. Do you see? Do you see? Do you see? What do you see? What about the c squareds? They cancel. So all of us can go cancel that one, cancel that one. Can't cancel on the third term, but it certainly looks prettier than it did before. So our new equation now looks like this. T0 squared equals T squared minus V squared T squared over C squared. Cool. Brandon, what does step 5 want me to do? Factoring. Math 9. Yeah, that's when you learn factoring. How do I factor out a t squared? Brandon, is there a t squared in this term? Say yes. Is there a t squared in this term? Say yes. It's a GCF. It's ugly. It's your greatest common factor, but it is a greatest common factor. So I can write this now as T0 equals t squared bracket. When I factor a t squared out of a t squared, what number is left behind? A 1. And then a minus, and then I guess a v squared over c squared would be left behind because I factored the t squared out. Math 9. And then I think once you've written that down, all of you are going to turn the page, yes? I'm going to just stay here so you can see where we left off. Yeah. What should be t squared? Oh, T0. Yeah, I left the squared off there. Thank you. Candy for you. Remind me to give it to you. Hey, it's Einstein. I'm allowed to make a mistake. Okay. And then Petco, what does it want me to do for step 6? I want to get the t by itself. Well, first of all, if I look at this equation, what's the bracket doing to the t squared? So how I'll move the bracket over. So I'll get this. The T0 squared would drop down like a domino. That bracket would end up on the bottom, and once it's on the bottom, I don't need to write the bracket because it's all in the bottom of a fraction. There's more than one thing. Brackets are implied. That equals T squared, except I want to get the t by itself. Right now I have the t squared by itself. How does one get rid of a squared, one wonders? So what I'd like you to do is put a square root symbol there, a square root symbol there, square root symbol there. I'm going to square root everything. What's the square root of t squared? Just plain old t. What's the square root of T0 squared? Just plain old T0. On the bottom, the square root doesn't cancel. So this gives us our time dilation equation. It says this. T equals T0 all over the square root of 1 minus, and then if you all look up for 1 second, instead of writing v squared over c squared, there's a better way to write it. I'm going to write it as v over c all squared. That should be the first equation on the back of your formula sheet under the special relativity section. Can you look at it and see that you know where it is so that you can find it? We call this the time dilation equation. Really what you'll have to memorize is what each thing means, but we're going to practice this quite a bit. What does each letter mean? Well, first of all, T is the time for the stationary object. What does the word stationary mean? What does the word stationary mean? Not moving. So if you want to, you can write for the not moving object, for the stationary or not moving object. And then you can put in brackets, usually that's going to be Earth, because most of the time we'll assume as our 0 reference point the Earth back home when we're traveling in space. T0 is also time, but T0 is the time on board. That's how I remember T0, T-O, on board. The moving object, the spaceship. the particle inside the particle accelerator, the really fast jet, the moving object, whatever it is. Time on board the moving object. V is the speed of the moving object. How fast the spaceship is moving. How fast the particle inside the particle accelerator is moving. How fast the satellite is moving relative to the Earth. And, what does the letter C stand for? Not the something of light. Speed of light. In our notes today, I'm going to encourage you to write everything and show all your steps. But I'm also going to say, as you get good in your homework, if you want to try taking shortcuts, I have attached the answers, and I'll put a full answer key showing all my steps online. Feel free to see where you can cut corners on your calculator, how much you can do on your calculator and still get the right answer. But on a test or a quiz, we're going to write everything out. And the first few times on our calculator, I'm going to have all of you follow along, because I know I can teach you a method that will work for every calculator in this room. And then you can start to take shortcuts for your specific calculator, especially those of you that have the two-line fraction displays have some really nice shortcuts you can take. Example 1. Suppose a spaceship is traveling at 85% of the speed of light. If 1 year passes on the spaceship, how much time passes back on the Earth? Aiden, what's this question asking me to... Aiden, I was right. What's this question asking me to find? Time. Which time? T0 or T? And that's what you have to be able to figure out. Pardon me? Time back on Earth? Yes. So let's write down T equals question mark. That must mean they told me time on board the spaceship. Aiden, how much time went by on board the spaceship? One what? One of the nice things about Einstein's equations, they are unit independent. If you put in years, you'll get back years. If you put in seconds, you'll get back seconds. If you put in hours, you'll get back hours. So we don't have to do conversions. I'm going to put a time in years, and I'll get an answer back in years. So time is 1. And remember, the proper abbreviation for years technically is a lowercase a for annually. For annually. Because Y is taken by stupid American yards. V. How fast are we traveling? Aiden, can you read me the phrase after the word at? Say that again, please. And you're correct. Say it one more time, not to make fun of you, but to emphasize it. Stop. I told you this was Math 8 and Math 9. We don't do math with a percent. We have to change it to a decimal. So 85% is what as a decimal? It's Math 8. Okay, 0.85, you divide by 100. Most of you will do that step in your head. Good, although you can use your calculator. Okay, so 85%. What's the next word? Starts with the letter O. Stop. The word of in math. What? Who? Did someone teach you that? Who taught you that? Someone here? Good, because I've been trying to get that across to kids. Of means multiply. The only time of doesn't mean multiply is if you go 2 to the power of 5. That actually means 2 times 2 times 2 times 2 times 2. It doesn't mean 2 times 5. Anywhere else, and I've looked, everywhere else where I see the word of, I can just replace it with a times. So we have 0.85 times, keep reading. 0.85c. That's 85% of the speed of light. That's the symbol for the speed of light. We use the letter C because light is a constant. It's the universal constant, and so we chose the first letter of the word constant as its symbol. The same way a lowercase g is what we often use for the acceleration due to gravity. It's just a symbol. As a magnitude on your formula sheet, what is it? It's in the special relativity section. You have it open to the back page. It's the first thing I gave you. It's how big is c as a magnitude? 10 to the 8th meters per second. But hold off. Let's write down our time dilation equation. So the time dilation equation says t equals t0 all over the square root of 1 minus v over c all squared. Is that okay? By the way, what if I wanted to find t0? How would I get the t0 by itself? What's the square root doing to the t0? Dividing, so how will I move the square root over? Let's come back to that, but this equation, again, like all equations, there's several equations in one. Aiden, what did you say t0 was? One minus, what was v? 0.85 c. And then there would be another c on the bottom from the equation, and that whole thing would be squared. Ooh! Aiden, do you see? Do you see? Do you see? What do you see? We set it up this way. This is going back to your question, Cal. We set it up this way on purpose as a percentage of the speed of light so that those c's would cancel, which makes my math a lot easier. In fact, in the brackets, it's just 0.85 squared. And now we're going to go to our calculator. Everybody pick up your calculator. Clear your calculator. There are shorter ways to type this that you can discover on your own, but the method that will always work is if you start with the squared term. If you go 0.85 and hit your squared button, equals. And then if you go 1 minus that thing and hit equals, what is the 1 minus all inside of? So if you go square root, answer button, and hit equals, you 0.52678, that there. Oh, it's 1 divided by that. So 1 divided by answer button. And you should get almost exactly 1.9 years, not quite, like 1.89 something, I think. If you didn't get 1.8983159992, if you got something wonky, don't freak out yet. Follow along carefully on the next one, and if you get it wrong, then I'll come and look over your shoulder. But for starters, Aiden, 1.9 years. Almost 2 years, almost a 2-to-1 relationship. So you went on the spaceship for 1 year, you went out for 6 months, turned around, came back for 6 months, there's your 1 year of travel, and when you got here, we would say, oh, no, it's 2021, not 2020. Your clocks would say 2020. Our clocks would say 2021. It gets weirder. But cooler. But weirder. But cooler.
But if you were to go there, that
Patience. Hold the question. I'm going to answer some of that. You're going to ask a good question, and I think I know where you're going, but ask it after this example. And this is the time to bring deep questions. We're going to get into some weird stuff. I'd like you to imagine all of you are astronauts, and you're all 30 years old, and you've been given a once-in-a-lifetime opportunity to go on a space voyage, but it means leaving behind your 5-year-old daughter. You're going to go in the year 2000. Why in the year 2000? I wanted to keep the math nice. I know the year 2000 is a while ago, but just to make the math easy. And you're going to travel at 0.99 c. What percent of the speed of light is 0.99 c? Okay, or 99% of the speed of light. And you're going to travel for 6 years as measured by you in the spaceship. You're going to go out for 3 years, turn around, and come back for 3 years for a total of 6 years. In other words, T0 is 6. How much time will have elapsed when you return from the frame of reference of your young daughter who was left behind on the Earth. What's this question ask me to find? Time. Yeah, T or T0? Which one? T? Marcella, that's a long blink. You going to make it? Because it's going to get cool. Psych yourself up. Marcella, what is T0 then? Good. What's V? 0.99 C. Our time dilation equation says this. T back on Earth equals T0 all over the square root of 1 minus... Mr. Dueck, is there a shorter way to write some of this? I will teach you in a couple of days how to abbreviate this, but I'm going to leave it long right now so you can see how well it fits together. In fact, you'll see I gave you a way to abbreviate this on your green sheet already. Marcella, what's T0? All over square root of 1 minus... What's V? It's not 0.99. 0.99. Don't forget the speed of light in there. All over C, and it's this whole thing squared. Marcella, do you see? Do you see? Do you see? What do you see? C's cancel. So now get your calculators out, folks. Okay. Marcella, you and I are going to do this together. You're going to go 0.99 squared. It equals 1 minus that. So 1 minus answer button. It equals square root of that. It equals 6 divided by that. How many years went past back home on Earth, Marcella? So let's look at this. Here's what this means. Having left Earth in the year 2000, you would return to Earth in Earth year 2042. Somewhere around June, if I really wanted to be halfway through the year. How old will your daughter be? Marcella, how old was your daughter when you left? How many years went by for your daughter? 42.5. So your daughter is 47.5 years old. How old will you be? How old were you when you left? 30. How many years went by on your spaceship? What was T0? 6. And you will return home 11 years younger than your daughter. And that's not fancy numbers. That's how the universe will work if we travel fast. If you saw the movie Interstellar, they were trying to get some of that across in that movie, except there, the time dilation was due to general relativity. Gravity also slows time down, so when you're near a black hole, time would be moving way, 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 way slower, and so that was most of the time dilation there. But the plot of the movie was the father came back to find his daughter, an old woman. Right? Pardon me? I don't have a kid. Well, really, the question then is that you asked a great question. If we remove Star Trek, Star Wars nonsense physics, if we stay in the real universe, space travel will be one way. You'll send colony ships where the whole family and spouses, all the loved ones are going, or it'll be people that want the adventure, that have no spouses, that have no kids, that just want to go out there because they have no attachments back home. That's the clientele you'll get. You had a good question.
What I was going to ask is, wouldn't you reverse it coming back?
No.
Unless you took years and years?
No. Because it's the speed that you're traveling relative to the Earth. If you're moving relative to the Earth, whether it's towards it or away from it, doesn't matter. The time dilation will occur because you're moving relative to the Earth. That's why when you didn't see this. Let me pause the video for a second. We have to take this into account with GPS. I talked a little bit about GPS the other day, but put your pencils down, look up. Example 3. Let's do a little back to the future time travel. Let's travel into the future. Suppose a spaceship is traveling away from Earth at 99.9% of the speed of light. Back on Earth, 1,000 years pass. How many years elapsed for those on the spaceship? So we want to go away and we want to come back, and we want to come back in the year 3019. For how long on our spaceship do we need to travel? What's this question asking me to find? Which T? T0, time on board. Okay. So this wants me to find T0. What's T then? Oh, T is 1,000 back on Earth. What's our speed? .999 C. Yeah. So look at your green sheet. Look at the time dilation equation. I want to get the T0 by itself. Well, what's that square root doing to the T0? So I think if I want another equation, T0 is T times the square root of 1 minus V over C, all squared. Time on board the spaceship is going to be 1,000 square root of 1 minus 0.999 C all over C squared. Carter, do you see? Do you see? Do you see? What do you see? No? Callum, do you see? Do you see? Do you see? What do you see? Got to be paying attention here, folks. I've done it every time. What? The C's cancel. Do you see? Do you see? Do you see? What do you see? You didn't pick up on that joke, did you? Wow. Wow. The C's cancel. So now go to your calculator. You can type this in however you want if you want. You're going to get something in the 40s if you've done it correct. If I was typing this in, I would go 0.999 squared, 1 minus that, square root of that, and then that number times 1,000. And you should get 44.7 years. See if you get that. And then if you have that sitting on your calculator, divide it by 2, please. Is it probably 22.35? So you would have to head out for 22.35 years, turn around, come back for 22.35 years. And if you left in the year 2019, you would arrive in the year 3019, which sounds kind of neat until you really think about it. Traveling into the future, not so good. Imagine someone from the year 1019 beaming into present day. Would they function very well? Would they really enjoy things? I mean, they might for a little bit be, ooh, hot water, haven't seen hot and cold running water. That's kind of cool. But I mean, they wouldn't know the language. They wouldn't know the culture. They probably haven't built up immunity to certain diseases. I don't think it would be as fun in real life as we like to kind of romanticize. 5 years into the future, maybe, but 1,000 years into the future, nuh-uh. Mr. Dueck, yes, mentioned. Can you travel into the past? No, you can't. Or can you?